just to recall what all these things mean. So we're being asked if all these expressions here make sense. So let's start with div grad f. We see that the divergence of the gradient of f, it's actually the same like as this dot product, right? Del dot del f. And so if we think of del as a vector, then actually really this is just a dot product. And actually it's a dot product of two vectors really applied to f. So that's totally sensible. And actually how you would explicitly write this as well, it's just this dot product. So it's just this Laplacian expression. And so you apply each of these second derivatives to f and then sum them. So that's a perfectly fine expression. The next one is curl gradient f. And it's also good to think of it again as a vector. So this is actually just a cross product applied to f. And so actually this is equal to 0 because these two vectors, if you think of them as vectors, are actually parallel. And the next one is curl divergence of f. Now this one we have a problem because this is actually a scalar, right? Because this is actually px, qy, rz. So this is actually just one function. And so the curl, remember, it's a cross product. So now effectively we're taking the cross product of a single function. And so actually this does not make sense. Next one we have is gradient f dot g, but actually the gradient only works on functions. It does not work on vectors, at least in this class. How about the divergence of f times the curl of g? Oh, this is okay. Really, this is just a function times a vector. And you can certainly do something like this. You just distribute. On the other hand, this one, curl f cross g, this is also okay, because this is basically a vector cross another vector. And the cross product is actually well-defined precisely on vectors. So there's just no problem here. So right now I'm on Judith Arm's old final exam. So I think I had a few questions here. They're pretty good. Let me just go through number 7. There's a nice subtlety here for number 7 that I just want to briefly talk about. So let me just write down, let me just unpack what all this stuff here means. So S1 is the top half of the cylinder. S2 is the disk. And it says that both surfaces are oriented up. So this is an important technical detail. Notice how it's not outward. So if we were using the outward orientation, it would look more like this. So notice the problem here is with S2. And so, as you can imagine, there's going to be a sign. So, and let me just, they put E as that region on the inside. So I'll just denote it. So now F is just a vector field, so we're going to integrate it probably. And ignore the jibber jabber. And so explain why this following equation holds. So let's just write that equation down. F dot ds equals and then F dot ds. Okay, now what's important is we need to label these regions. So S1. Okay, and the key point that might trick you is that there's a plus sign here. This plus sign, the origin of this is this silly orientation of upwards. So here's what we do. We first do it the right way. And then we'll switch the signs. We'll switch the orientation of S2 and add a minus sign. Okay. So what we'll do is we'll start with, this is the correct way to formulate the problem, where everything is outward. We like outward. We don't like mixed orientations like this. So let's say we're doing this the right way. Just in order to differentiate this, I'm going to put bars over everything. Okay, so here's how we do it the right way. We're going to use the divergence theorem. So if we start with that triple integral, if we use the divergence theorem, we end up with the boundary of that region. So now what we'll do is we'll naturally split it into S1 and S2. So there's going to be an integral over S1. And remember, I'm using the bars because I'm trying to differentiate it from the bad formulation to the left. And then there's going to be an S2. And it'll just be the same integrand. Okay, so this is the correct way. So we actually have something similar above. Notice how this will correspond to the left-hand side, and we'll have the correct S1. So the only problem, as you can see, is the S2. So we have to make sense. We have to justify why there's a plus sign here. Because if we move it, if we put this S2 on the same side as the divergence, so if we rearrange, then we end up with that integral over S1 bar of f dot ds. We end up it's equal to that triple integral plus, I'm sorry, minus, that's the whole point, minus that S2 integral. Okay, so we have to justify minus integral of S2 bar. Remember, the bar just indicates that it's the correct outward orientation of f dot ds. We have to say why this is equal to plus sign. And remember, this is now using the inward. This is the bad one that we were given. Okay, so so really what's going on here is we have to use the normal vectors. So this is, remember, ds is shorthand notation for f dot n times the area, surface area element. Okay, now the key thing is that these are two different normal vectors. So the normal vector for the outward is actually the negative of the normal vector for the inward. And so then we get two minus signs. And so this is exactly the positive sign that we want. Okay. So this problem just shows that you have to be careful about the orientations and just always, always, always think outwards. Okay, the next one I want to talk about is number 5. So our f is given by x, y, z, and our s is given by paraboloid thing. So it's x equals 1 minus y squared minus z squared, and we're supposing that x is greater than 0, z is greater than 0. And 0 is less than y is less than z. Okay, so let's try to unpack what all this means. First of all, just because this is a little confusing, we're asked to compute an integral. So actually, I'm gonna relabel things. So because we want an integral, we can relabel coordinates. You don't have to do this. This is completely optional. But for me, I'm so used to thinking of z as the function that it makes me a little more comfortable to put it there. So what I'm going to do is I'm going to say, how about we change x to z, and we'll change, let's say, z to x, and we'll change y, and we'll just leave y as is. Okay, so if we do this, our f is actually not as good looking. It is z yx. So we were tricked. We thought it was the best vector field possible, but actually in disguise, it's not. So then our z is 1 minus x squared minus y squared. And now our ranges are positive z, positive x, and still y is less than x. Again, you don't have to do this, but this makes things a little clearer for me, what's going on. So let me just draw what's going on here. So I'm going to first plot z versus r. So it's 1 minus r squared, so I'm going to have this paraboloid. And because z is positive, we know it's just the upper part. And then I'm going to draw the xy plane. And we know that x is positive, so we just need this part of the plane. And we know y is less than x, so it'll be this region here. And I suppose we also know that because if we look at this intersection point here, really this corresponds to r equals 1. So I guess we also have to restrict to this part here. I think this is our region of integration. It doesn't look pretty. I'll totally give you that. But the key observation is that this is actually just pi over 4. This is theta equals pi over 4, and this is theta equals 1. So really, in polar coordinates, this actually is not that bad. So what are we asked to do? We want to compute the surface integral part of the surface. Yeah, so we're asked to compute the surface integral over this surface. And the surface will be defined over this coordinate region here. So just to indicate it, it'll probably be something, it'll be like this part. Because remember, x less than 0, we don't want. So one way you could try to do this is Stokes theorem, I suppose. But I don't think Stokes theorem is the right way to go here, because the boundary of the surface is kind of strange looking. Right, because I'm going to try to draw this in 3D really quickly. Emphasis on try. Let's see how well I can do this. So we're defined on this wedge here. That's really what's going on. And so it looks sort of like this. So if you look at that boundary, because remember Stokes theorem, it says that surface integrals, they correspond to line integrals on the boundary. That does not look good. So on the other hand, if we had, if we were defined everywhere, then our boundary would actually be the circle, and that would actually be quite good. So I would say this is a good boundary, because it's just x squared plus y squared equals 1. But this is a bad boundary. And so I would say Stokes is actually harder. It makes your life harder. So I would actually just do the surface integral in polar coordinates. So like as I outlined, theta, it just ranges from 0 to pi over 4. R just goes from 0 to 1. And so of course our z is given for us here. Our z is given by 1 minus r squared. And so we'll be doing, our integration variables will just be r and theta. And so then we'll just have our integrand, which will look like theta. And then we'll have our integration ranges going from 0 to 1 and 4. And I think that we'll just be making sure you can compute this thing. But I think because 1 minus r squared is pretty simple, I don't think that'll be a huge deal. Like don't automatically go for Stokes theorem, because it's not always a good idea. what we're looking at here is there's a lot of stuff going on in this problem. So one claims that the curl of this thing is 0. Another is that the divergence of this is 0. And apparently, what's going on is the flux integral is actually 0. If we look at the sphere centered at 2, 2, 2, that's an oversimplification of what 2, 2, 2 is, but you get the idea. And let's see, let's just label that as S. Okay, and then we'll and finally, there is no vector field, so it has a curl. So let's see how far we can get through all this, because I say this is by far the most important example you might see in this course, because this thing right here, if we write it as r divided by r cubed, remember this is 1 over r squared. So this is actually the gravitational force. This is also the electric field of a point charge. That's very interesting. So the curl of f equal to 0, I think we may have done this on a homework problem, so I'm not sure I should spend time on this. And we may have done this we may have done the divergence also. So I'm tempted to skip to number 3. Let's go to number 3 really quickly. So if we do f dot ds, then the key thing to notice is that the singularity is here. Whereas this sphere here, it avoids the singularity. Okay. So yeah, we're allowed to use the divergence theorem, so that's good. So now, because it avoids the singularity, we can use the divergence theorem. So that's 0. And the whole this might seem obvious. Like, we already know the divergence is 0. So why isn't that 0? Why would we expect anything else? Well, the funny thing is that if you look at this sphere and you take that integral, it's because the singularity is inside the sphere. We actually no, I think I did that in a lecture. But really, you can think of this as a single point charge. So I think let's now move to the gradient. So in other words, we should have fx, fy, fz equal to xyz divided by x squared plus y squared plus z squared. So if we do the x part, for example, then really what we do is we just integrate those things. So f is the integral. And I think because we're holding these things constant, I'm just going to call that c squared. Okay, so I think that's actually just negative. I think that's just negative x squared plus c squared, right? Plus that integration constant, right? Because if you differentiate this, we should get, by the chain rule, we should get something like this, right? So I think that works. And how did I guess this? Really, I kind of knew the answer already because it's a dimension thing. So if we go back here to see it's 1 over r squared, it's very tempting to just say the gradient is just one. If that thing is the gradient, so in other words, if df dr is 1 over r squared, you would be tempted to say that f is just minus 1 over r. It turns out that's exactly what it is. So remember, this is 1 over r. And so it turns out that you can actually share the c1. The c actually you'll eventually go to 0. You have to do the fy and the fz parts, of course, but it turns out this is all you need. And this thing, yeah, like the reason I'm going over this kind of simple examples is because they're the most important. So let me just talk briefly about why this thing does not have a curl. Okay, so we actually know that the divergence is 0. And I did tell you that if this is true, then it should imply that f has a curl. But the key thing is that this is true if you have a domain without holes. But if we look at the function, it's r divided by r cubed, we notice that r cannot be 0. So the origin is a hole. So this theorem of F here is not valid. And in fact, it's not true. It's not true because if it were true that it had a curl, then we could take that surface integral. Let's just call this thing S1. That sphere. So we could take the surface integral. We would use it to curl. And let me emphasize that this is closed. And so by Stokes theorem, it's actually equal to the integral over the boundary. But notice that the boundary of the sphere is 0. There is no boundary. right? So we would conclude that this flux integral is 0. But this is not 0 because it has to include the charge. It has to include a point charge inside of that sphere. So in other words, our assumption here that there is a curl, it can't be valid. Okay, so and I'll just give some free information. I like functions like this for there's some other ones like that I think I mentioned along the way. Things like minus y x divided by x squared plus y squared. Functions like that are pretty good. I think we have time to go over a couple more of these things. Okay, let me just, I think this is important to mention when you should use divergence theorem, integral theorems. Sometimes you don't want to do these things directly. So let's consider this example. This is in, okay, what's the f here? 1 plus 3y squared minus 6x and x minus 3z squared. Okay, they're trying to tell you what to do. They're trying to tell you to do divergence theorem. So the s is x squared plus y squared less than or equal to 9, and looks like z range. Find the parts. Oh, I'm sorry. Find the flux across S. So we want the flux integral of f dot ds. And we'll use the outward always. So S3, S1, S2 are given like that. So I'm mentioning this because do not evaluate directly. Highly recommend do not use surface integrals for this thing. So use the divergence theorem, please. That would take me quite a bit of time to do. So we'll just call that interior E, like they like to do. So del dot F dV. Okay, so the divergence is a lot simpler. So let's take dxp, dyq, dzr. So notice how this is 0. It's already looking better. And the next term is also 0, so that's not bad either. And then finally, we have minus 6z for that last term. So you can see that it is insanely easier just to do the divergence theorem. Okay. But the other, you'll notice that I actually said, where did I say this? I said this somewhere. Yeah, okay, I said it here. So the reason I said it in this problem is because, again, the boundary is bad. I said don't use the integral theorem, but in this case, everything got the domain that you transition to it's just an ordinary cylinder. So you can just use cylindrical coordinates for this. And then it's straightforward. Because the integrand, of course, is just 6z. It's simplified quite a bit. So, of course, in cylindrical coordinates, z actually, it doesn't do anything. So z stays the same. We're not using spherical. So in other words, what you'll have is you'll have something like r dr d theta d dz. And so this 6z, it'll actually factor out. So that thing, I think, is just, it's the area of a circle. So I think it's like 4 pi times r squared. Pi r squared. So, and then this, of course, will just be something like 3 c squared. So like I said, this it turns out that problem becomes really easy if you just do it using the divergence theorem and not with the surface integral. With a surface integral, this would be quite bad. Okay, let me talk about this problem really briefly. This is on Sam's website. And so S is the portion of the unit sphere above the xy plane oriented upwards. So again, I'm trying to simplify it, just doing a 2D representation. So it's above and oriented up. So this is S1 downwards. Whenever you see things like continuous partial derivatives, just ignore it. That's just jibber jabber that mathematicians like to do. So what is the relationship between curl F on S1 and curl F on S2? So curl F versus the S2 one. The thing here is, again, the orientation. That's why I'm bringing this up, because you have to keep track of these things to make sure you don't get things, you don't have a minus sign going around here. So the thing you have to keep in mind with Stokes theorem, which says that if you take any surface integral, not that you could rewrite it as that line integral. The thing you have to keep in mind is that there's an orientation. And you determine it by the right-hand rule. Okay, so if I use Stokes theorem for each of these integrals, we have to keep in mind what the line integral will look like. So for S1, using the right-hand rule, we see this is the correct orientation counterclockwise. It's positively oriented. But if I do the line integral for S2, if I use the right-hand rule, then my thumb is pointing downwards. So my fingers are curling clockwise now. So it's actually the opposite orientation. So whenever you have opposite orientations, that means you need a minus sign. So, but to clarify how it actually connects to S1, let's suppose for the moment that it had the correct orientation. So I'm going to redraw S1 and S2, but with the correct orientation. Not that this is incorrect. It's just the orientation that we want it to be. So we'll do up again for Stokes theorem purposes. So in this case, as long as these surfaces have the same orientation, we actually have that the S1 integral is equal to the S2 integral. I'm going to put a bar here. Just to indicate that's the different orientation. And so to convert it to this N1, we just add a minus sign. Notice I put no bar here. Okay, so really these things are equal but opposite. So these things have the opposite sign. And just to belabor this point slightly a little bit more, we can actually show this another way. So you can use the divergence theorem to prove this. So if I draw S1 and S2 like so, then they actually form a closed surface. Which is outward. So therefore, the integral of we're integrating curls, right? So therefore, the integral of that curl, well, it's the triple integral of the divergence of the curl. And if you take A dotted with its cross product, surely you should get the product is orthogonal. So this should be 0. So if you split this up and now, you get an S1 integral plus an S2 integral. So because these things are 0, surely we get S1 is negative S2. Okay, so that was just another way to say that. And I think that divergence theorem proof is a nice segue into the last problem I want to talk about. Let's do this really quickly. Let's show that the curl of the gradient is 0. And let's do it using a Stokes theorem way. So we want to show that the curl of the gradient is 0. So you could just do it directly. This is just a cross product of two things pointed in the same direction. So that surely that has to be 0. But you could also do it with Stokes. If we look at Stokes theorem, we'll get a line integral along the boundary of that surface. But notice this is a line integral of a gradient, so we can actually use the fundamental theorem for line integrals. I think maybe we call this the gradient theorem. This is f of x, or f of r, whatever, x, y, z, evaluated at the end. But notice the endpoints are the same because it's a closed curve. Because it's a closed curve. So we get that this is 0. So therefore, we know that this is 0. So therefore, this has to be 0. everywhere. Right, this is like saying that if you take the integral of f of x from a to b for all a and b, surely that means that f of x is equal to 0 everywhere. Right, because I can make that interval as small as I like. I actually like, I think this derivation is a little better. I think this is a lot quicker, and you don't need high-tech machinery like Stokes Theorem. But I thought it was another interesting way to do it. And it's I think it's specialized enough that where it's appropriate to be an exam problem.